Let's take a look at bonding in alkenes. We've talked about the structure of CC double bond in Chapter 1. We know that double bonded carbons, like this one, will be sp2 hybridized. So, sp2 hybridized carbon will be in trigonal planar shape, and the bond angle will be 120 degrees. And because sp2 has 33% of S, it has more S component compared to sp3 hybridized carbon, so the carbon will be more electronegative. The conjugated dienes will be slightly more stable than a single double bond. Why? So double bond is made of one sigma bond and one pi bond. Pi bond is formed by overlapping of the p orbitals side by side. Okay. When we have a conjugated double bond, this is what it will look like. All the carbon atoms will be sp2 hybridized. So on each of the 4 carbon atoms, there will be a p orbital perpendicular to the plane of the molecule. Each contains 1 electron. So these p orbitals, all 4 of them, can overlap with each other side by side. So as a result, those 2 pi electrons are not localized to 2 carbon atoms. They are delocalized to 4 adjacent carbons. So we have greater delocalization of the pi electrons. As a result, it's going to be more stable than a single double bond. Alright, next we will take a look at isomers in alkenes. So let's first use the 4 carbon alkene as example. There are 4 isomers for alkenes with 4 carbon atoms. So here are the structure of the 4. First, let's name these 4 compounds. The first molecule, double bond, is between carbon 1 and 2, 4 carbons, butene. So the first one is called 1-butene. Second one, we have a 3 carbon chain and a branch on carbon 2. So it's a propene and a methyl group on carbon 2, 2-methyl propene or 2-methyl 1-propene. Now for the next 2 molecules, when you name them, you see the double bonds are between carbon 2 and carbon 3, 4 carbon chain. So they are 2 butenes. You got the same name, 2-butene for both cases. But if you take a close look at the structure, you would see that they are not exactly the same. In the one on the left, the methyl groups are on the same side. The hydrogens are on the same side. The one on the right, the methyl and a hydrogen on 2 double bonded carbon are on one side. So 2 methyls are on the opposite side of the double bond. This is an example of a cis and a trans. When the 2 methyl groups are on the same side of the double bond, we call it cis. two methyl groups on the opposite side of the double bond, we call it trans. Okay, so cis and trans are the configuration of double bond. Cis 2-butene and trans 2-butene will be stereoisomers of each other. And from chapter 3, we talked about the stereoisomers. And we say enantiomers are mirror images of each other, but not superimposable. Diastereomers are stereoisomers that are not mirror images. So according to the definition of diastereomers, cis and trans double bonds are stereoisomers of each other, but they are not mirror images. So cis and trans double bonds will be classified as diastereomers. Okay. Well, the relationship between 2-butene and 1-butene will be constitutional isomers. Okay, same 1-butene versus 2-methyl-1-propene constitutional isomers. So next, we're going to introduce the easy notational system. Here, Z means atoms of higher atomic number are on the same side of the double bond, and E means the atoms of higher atomic number are on the opposite sides of the double bond. So basically, Z is pretty much the same as cis. Z is pretty much the same as cis, and the E is pretty much the same as trans. Okay? We use this easy notational system to define the configuration of double bond, just as we use RS to define the absolute configuration on the chiral center. Okay, so let's see an example here. So this is our cis 2-butene and trans 2-butene. Based on the easy notational system, we will call these two molecules Z2-butene and E2-butene. Now let's learn the priority rules to define E and Z for double bonds. The rules will be pretty much the same as how we determine the RS configuration for chiral carbons. The priority is based on the atomic number. But what you need to pay attention is that we will consider the two double-bonded carbons separately. Okay, don't mix them together. All right. So let's see the first example. Consider the double-bonded carbons separately. All right. So on the left side, what's attached to the double-bonded carbon are chlorine and hydrogen. Chlorine has higher atomic number, so chlorine side is higher and hydrogen side is lower. So we are done with the left carbon. Now let's look at the right carbon. Bromine and fluorine are the two atoms attached to it. Bromine has higher atomic number, fluorine has lower atomic number. So now we have these priorities. What I would like to do is to draw an arrow going from higher to lower. Okay, so that's what I would do. Higher to lower, higher to lower. Then you have two arrows. If these two arrows are pointing to the same direction, like in this case, they are pointing to the bottom, we say because the higher priority substituents are on the same side, lower priority substituents are on the same side, this double bond is in the Z configuration. Okay? More examples. For the left side double bonded carbon, the atoms attached to it are carbon on the top, H at the bottom. So carbon is higher than H. I draw the arrow going from higher to lower. On the right-hand side, the two atoms attached to the double bonded carbon are carbon at the top, carbon at the bottom. So we need to take a look at what are the atoms attached to those two carbons, similar to what you would define R and S configuration for chiral carbons. Anyway, for the top carbon, there are 3 hydrogens attached to it, so I put HHH in the parentheses. For the bottom carbon, there are 2 hydrogens and 1 other carbon attached to it, so I will put in parentheses CHH. List the atoms in higher to lower order based on atomic number. So the first point of difference is the H versus the C. C is higher, H is lower. So this is our arrow. Now the 2 arrows are pointing to the opposite direction, which means on one side the higher is on top, on the other side the higher is at the bottom. Okay, that's why this is a trans double bond, or the double bond is in the E configuration. Next example. On the left side, we have Br and chlorine. Br is higher. Here's my arrow. On the right-hand side, attached to the double bonded carbon are C and C. Then we have to look at what's attached to the C. For the top carbon, there are 2 hydrogens and 1 other carbon, so CHH. For the bottom carbon, there are 2 other carbons and a hydrogen, so CCH. Okay? The point of difference is the middle letter H versus C. So the the bottom part is higher, top part is lower. Okay, so here is the arrow. And because the arrows are pointing to the opposite direction, the double bond is in the E configuration. So again, similar to determine R and S configuration, you should consider one atom at a time. Don't take the whole group. Okay? So like in this last example on the right side, we have an OH group in the molecule. But we do not consider that O, because before we get to the O, we already have a difference. Okay? Next example. Alright, so on the left side, there are 2 carbon atoms attached to the double bonded carbon. For the top carbon, what's attached to it is CCH. For the bottom one, it's CHH. Alright, so here is the arrow going from the higher to lower priority. On the right hand side, there are 2 carbons attached to the double bonded carbon. On the bottom, we have Cl, chlorine, HH. And on the top, it's NCH. Okay, so we have N compared to Cl. Cl is higher, nitrogen is lower. The arrows are going to the opposite direction. The double bond is in the E configuration. Next example. On the left side, we have O and O attached to the double bonded carbon. What's attached to the O? On top, it's H, and bottom, it's C. So C is higher. On the right-hand side, what's attached to the double bonded carbon? C and C. So what's attached to those 2 carbons? At the bottom, we have double bond O, and we would consider whatever is on the other side of the double bond twice. So we have OOH for the bottom part. And for the top, it's OHH. And here are the arrows pointing to the same direction, so the double bond is in the Z configuration. Two more examples here. Now in this molecule, we have 2 double bonds. It's a diene. But only one double bond can adopt the EZ configuration. Why? It's the double bond on the left that we can have E or Z configuration. The double bond on the right, the last carbon in this chain, CH2. That carbon has 2 identical substituents. Okay, so the cis and trans stereoisomerism in alkenes is not possible when one of the doubly bonded carbon bears 2 identical substituents. Okay, so when they have identical substituents, there is no way you can define which is higher, which is lower, right? They are the same. Anyway, so the right-hand side double bond has no configuration. Let's take a look at the double bond on the left side. Okay. For the double bonded carbon on the left, we have H and C attached to it. So C is higher, H is lower. On the right-hand side, C and C. The bottom C has 3 hydrogens. The top C has CCH attached to it, right? So here are the arrows, and they are pointing to the opposite direction. Double bond is in the E configuration. Now let's see how to name this compound. This compound has 2 double bonds, so it's a diene. How do we number the carbon atoms? We want to give the double bonds the lowest possible number. So we will start to number the carbon chain from the right-hand side. Okay. Double bond is on carbon 1 and carbon 3. Carbon 3 has a methyl group. So the name is 3-methyl 1,3-pentadiene. Don't forget the configuration of the double bond E. We put E in the front in parentheses, just like we put down R or S in the name for chiral centers. And here we have only one, even though we do have two double bonds, we have only one letter E in the front of the name, indicating only one double bond can have this E or Z configuration. Okay? Next example. This is another case that we have two double bonds, but the one on the left carbon is CH2. It has two identical substituents, so this carbon cannot have the E or Z configuration. This double bond cannot have the E or Z configuration. It's the double bond on the right-hand side that can be E or Z. So let's take a look. On the right side, we have Br and H attached to the double bonded carbon. So Br is higher, H is lower. On the left-hand side, C and C. The top C is attached to CCH. The bottom C is also attached to CCH. Okay, so we have the identical groups. Now we need to move on to the next carbon. Okay, so for the top part, if we move on to the next carbon, we have HHH attached to that carbon. For the bottom carbon, there are two hydrogens attached to it, but it's a double bonded carbon. So what we would do is to consider the previous carbon once, only once. Okay, so what we have here is CHH. Okay, we need to find 3 atoms that's attached to it. That's why we need the previous double bonded carbon once. Okay, so the bottom is higher than the top, and the arrow goes in opposite direction. The configuration for this double bond is E. How do we name the compound? It's a diene, so we have to include both double bonds in the parent chain. It's a 4-carbon chain, okay? Even though we have a 5-carbon chain, but keep in mind, double bond takes higher priority. All right? So here's how we number the carbon chain in order to give the substituent at a lower locant. 4 carbons, 2 double bonds, butadiene, 1,3-butadiene. Carbon 1 has bromine, carbon 2 has an isopropyl group. So the name for the compound, 1-bromo, 2-isopropyl, 1,3-butadiene. And don't forget to put the configuration E in the front of the name.